All right, I'm back. We're actually going to be on page 296, but I am currently on page 295 because the thing we're going to talk about is really based on what we did on 295. So I just want to highlight some of the things here. When we found the derivative of x to the first, we got 1, right? And you actually knew that because y equals x is a linear function, and the slope of that function is 1. And so you knew that the derivative would be 1 because the slope and the derivative are the same thing. So like that one made sense. But what I'm going to do is I'm going to rewrite that as d dx of x to the first is 1 times x to the 0, which happens to be 1. Then we found the derivative of x squared. So we found d dx of x squared, and we got 2 times x to the first. Okay. The derivative of x cubed we found to be 3 times x to the second. Then we started to suspect there's a pattern, right? The pattern appears to be take the exponent, bring it down as a coefficient, and then subtract 1 from the exponent. So we go x to the fourth becomes 4x cubed, x to the fifth becomes 5x to the fourth, x to the sixth becomes 6x to the fifth. We think that the pattern would probably tell us that the derivative of, let's say, x to the 200th, which I would never want to use the limit definition on, right? You would need the 200th row of Pascal's triangle. Where are you going to get that? Even if you got that, do you want to do it? No. So I think it's going to be bring the exponent down and then subtract 1. So we think that's our pattern. It turns out that is definitely our pattern. So here is what the pattern is called. So the pattern is called the power rule. So the power rule is a really big deal. And the power rule is going to let you find the derivative of power functions. But no one probably ever told you that they were called power functions. So if you have a variable, a single variable, to a real numbered power, that's called a power function. So to find the derivative of a power function, you can use something called the power rule. The power rule says for all real exponents n, the derivative with respect to x of x to the n is exactly what we thought it was. Bring the exponent down, subtract 1. Bring it down, subtract 1. Bring it down, subtract 1. So it applies to any real number. So if I wanted to find the derivative of x to the pi, pi is a real number. So this should be pi x to the pi minus 1. And that's it. Now, something like e to the x, not a power function. That's actually an exponential function, right? Funct, F-U-N-C. I don't remember. I think I usually F-U-N-C period. I don't know what I did there. This is actually an exponential function. It's not called the exponential rule. It's called the power rule. So power rule does not apply. Power rule does not work. Does not work. So the type of function you're dealing with is going to matter, right? So then there are a couple of things here. So the rule is being applied to x with a coefficient of 1. So it's way more complicated if you have something like 3x minus 5, the quantity 3x minus 5 to the fifth. That's not a power function. The power rule doesn't apply. Furthermore, it works for any variable. So it could be, as long as you have a real exponent. So you don't need, you could do like dz of z to the 7th, right? So z is the independent variable. So the derivative with respect to z makes sense, will be 7z to the 6th. All right, let's do a couple examples. So the first one is just like that example I started with, x to the 200th. Nobody's using the limit definition on that. Like, no one is using the limit definition on that. This will just say that dy dx should be 67x to the 67 minus 1, which is 66. Not bad. Power rule is your friend when it comes to taking derivatives. It's probably the most commonly used rule, and that's great. So here, you do have to get used to working with fractions again, like you were in 5th grade or whatever. So let's say f prime, because it's called f of x, is, all right, so we're going to bring the exponent down. So it's going to be 23/7 x to the 23 over 7 minus 1. So I'm actually going to write that this time. And then we'll simplify that. So 23/7 x to the 23 minus 7 is 14, 15 is 16. Whoops. So this will be to the 16/7 f prime of x is 23/7 x to the 16/7. It's not pleasant, but like, how would you even use the limit definition? Like, you're going to try to rationalize or something? What do you rationalize with? Power rule is saving us there. All right, so these are the enemy, right? So let's make a note of that. Let's do it in a funny color. Radical notation is the worst. It's the enemy. All right, so as soon as you see radical notation, you're going to rewrite it using rational exponents. So let's do that in a friendlier color. You're going to want to use rational exponents because exponent, I don't know, I probably spelled it in there somewhere. All right, so here we're going to rewrite this as f of x is, so not f prime, we didn't find the derivative yet, so it's actually going to be x to the 3/14. Okay, so it's like the 14th root of x cubed, so to the 3/14. F prime is going to be 3/14 x to the 3/14 minus 1. So 3 minus 14 is negative 11/14. And you're just going to leave it that way. So leave this. It's only when you're like if you're matching multiple choice answers, then every once in a while you're going to want to actually like rewrite it from rational exponents back to radicals. But in general, as soon as you see a radical, turn it into a rational exponent. It's going to make your life way better. So what else we got on this page? A couple rules. All right. If we have a function f plus or minus g of x, if that function is differentiable, if f and g are differentiable, then f plus or minus g is also differentiable, and it should really say plus or minus. The derivative of f plus or minus g, let's put that in, plus or minus, is f prime plus or minus g prime. Derivatives are limits, so the limit rules basically will always apply to them, right? So we're saying f prime exists, which means the limit as h approaches 0 of f of x plus h minus f of x over h exists. G prime exists. The limit as x approaches 0 of g of x plus h minus g of x over h. That exists. So if we are adding them or subtracting them, just find the derivatives and add or subtract them. Also, there's this constant multiple rule. You're going to use this a million times and never even think about it. It's just saying that if you have a number times a function, and you take the derivative, then you get that number times the derivative of the function. Not really a big deal. These are called the sum and difference rules, constant multiple rules. There's only so many rules. We also know the power rule. So we have power rule, sum and difference rule, constant multiple rule. That's 4 rules already. There's only 3 more, really, and kind of a 4th, but like not really. All right, let's see if we can do this. Find the points on the graph where the tangent line is horizontal. Graph the function in an appropriate window, trace the values you found, confirm you're right. Okay, so tangent line being horizontal is a super common question because it relates to some very specific thing. So if the tangent line is horizontal, so what does it mean for a line to be horizontal? What is the slope of a horizontal line? It's 0. The tangent line is horizontal. That means that g prime of t in this case is also going to be 0. So we're really just going to find the derivative and set it equal to 0 and see if we can solve. So g prime. All right, so let's use some of this information that we've learned. The derivative of t cubed by the power rule should be 3t to the second. Okay. The derivative of negative 12t, so you could think of that as a linear function, and the slope of a linear function is just the coefficient of the variable. So it's negative 12, or you could think of that as using the power rule. So if that's the power rule with the constant multiple rule, the derivative of t is 1 times t to the 0, which is just 1, and then times negative 12. And then the derivative of 4 is 0 because it's a constant. The derivative of a constant is 0 because it's a horizontal line, so the horizontal line is 0. So this is our derivative. So then g prime equals 0 would mean that 3 times t squared minus 4 equals 0. 3 times t plus 2, t minus 2 is equal to 0. Okay, so we're looking for where it's 0. So that's at t equals -2 or t equals 2. All right, I want to extend this problem a little bit. So let's think about the sign of g prime. So I'm going to make a sign chart for g prime. G prime, you want to label it. I'm going to say -2 and 2, right? All the zeros of g prime are on here. If there are any discontinuities on g, I would put them on here as well because weird things can happen to discontinuities. So we get -2 and 2. Now I'm going to test regions, right? So I'm going back to, basically I'm testing them in this form because it's factored. So -1 billion would be a negative times a negative, times 3 is always positive, so it's really positive, negative, negative. So that's a positive overall. And then between them, like 0, for example, would be positive times negative, so negative overall. I actually think, I look at that and I see that that's a quadratic. The g prime is a quadratic that opens up, which means that the value should go positive, negative, and then positive again. But if you plug in a billion, you'll also see that you get positive. So what have we said about when g prime is positive? What does that mean about the function? It means the slope of the function is positive. If the slope of the function is positive, the function is increasing. So I know that g of x is going to be increasing, then decreasing, and then increasing. What's true about a point at which a function changes from increasing to decreasing? Well, if the function changes from increasing to decreasing, the function must have had a maximum. That's the only way that could happen. So I'm thinking that, let me change colors here. I'm thinking that g has a maximum at x equals -2. And kind of relatedly, if the function changes from decreasing to increasing at a value, it should have had a minimum. So I'm thinking that g will have a minimum at x equals +2. And I kind of think that the function is going to look like, I think it's going to look a little like this. I think this is what our function will look like. And I think that this is going to be at -2g of -2. And I think this is going to be at 2g of 2. And I think that if you wanted to, you could put in like a horizontal tangent lines there. Just kind of see what it looks like. And now what I'm going to do to wrap up the video is I'm going to switch over to the calculator and graph this thing and see what happens. So switch into a calculator page. And I need a new document. Add a graph page. You can't graph with t, so I'm just going to use x's. So x squared minus x cubed rather minus 12x plus 4. And let me zoom out. So I can just grab this. It's pretty easy to do. It's definitely not easy to do on the handheld. Let me zoom box here. And let's see if like the amount of calculus that we already know allowed us to get this. Let's find this relative maximum, which is what I was expecting there to be a relative maximum. I think that it's going to be at x equals -2. Nailed it. All right, let's do the other one. We're looking for a relative minimum. So relative minimum just means the minimum on an interval. It's not like necessarily the overall minimum for the function. And that happened at 2. It's almost exactly what we were expecting. Also, as we move from -infinity to -2, the function is increasing. We saw the derivative would be positive, which makes sense. Between -2 and 2, we saw the derivative would be negative, and that meant the function should be decreasing. That's what we have. Between 2 and infinity, the function should be increasing because we found that the derivative was positive, and that's what's happening. This is pretty awesome. So I'm going to go back to the notes because for some reason I like to end on the notes. Why? I don't know. Kind of started that like 70 videos ago, so I think I'll just keep it up. Here you go. That's our graph. It looks a lot like the calculators. We didn't bother to find g of -2 and g of 2, so like it's not as accurate, but like pretty good. And we just used the calculus that we so far know and we're going to know so much more before this is over. So we're on our way, and I'll see you in the next video to learn even more. So see you then.